All right, ladies and gentlemen, welcome back to another video with Mr. Kenton here in AP Chemistry. We're moving through Unit 5. We're now in Section 5.8, and we're going to look at how our understanding of mechanisms help us understand something about rate laws, right? Because really the reason why we've been having this conversation about mechanisms and all this is to get it to how do we look at a mechanism and use it to be able to tell us something about the overall rate law, or what's going to govern the rate of this particular process. And that's what mechanisms are going to allow us to do, is essentially to be able to support or disprove a mechanism, right? That is, hey, this is suggesting and providing evidence for a specific way the reaction carries out. This one supports that process. This mechanism provided doesn't support that, doesn't match up. So we're going to not use that mechanism. We're going to say that that mechanism doesn't represent how this reaction proceeds, right? So let's kind of dive in, right? Now, we saw in the previous section that we can have steps that are going to be slower or faster than others, right? You saw the designation of slow step versus fast step. And the reality is the slow step is going to be something that's going to limit your overall reaction rate, right? Think of it as in a relay race, right? You're only as strong as your slowest person, right? So you could have a whole bunch of people who run really fast, but then you have one person who runs really slow. That's going to offset the work of the other three. And so the same thing is true within mechanisms. You can have really fast steps, but the reaction is really going to be determined and based on whichever step is the slowest, which we call the slow step or the rate determining step. And like I said, it's also referred to as the rate determining step. And so what we're going to do is when we look at a mechanism, we're always going to look at the slow step and try to figure out, according to that slow step, because it's an elementary process or an elementary reaction, what's going to be the rate law according to that slow step, right? And so we know that the steps are going to govern the overall rate law for the overall reaction. Now, let's revisit our example that we looked at in the previous section, right? We saw that we had the reaction of nitrogen dioxide and carbon monoxide to make nitrogen monoxide and carbon dioxide, right? And so in this example, we had our slow and our fast step. Because those are two elementary steps, our rate law would be based on our slow step, right? That's our rate determining step. And so our rate law would be rate equals K times NO2 squared. Remember, we're using the principles of it's an elementary step, so we can use the stoichiometry of that elementary step to come up with a rate law. And we say this is theoretical because it's according to the mechanism, right? We haven't done any experimental data. We haven't checked it. And so it's theoretical, right? Now, let's say that you do an experiment and you carry out that experiment and we find out that the rate law is second order with respect to NO2 and zeroth order in respect to carbon monoxide. And so we get a rate law for this overall reaction to be K times NO2 squared, right? So in this particular instance, our experimental rate law and our theoretical rate law are consistent with each other, which is a good thing, right? And so because they're consistent with each other, what we would say as chemists, and what you guys need to understand, is that this mechanism that we've provided, it supports the reaction being carried out in this manner. This is a possibility for how this reaction can be carried out. It doesn't prove that this is the way that the reaction is carried out, but it gives us an insight. This is a way in which it can be carried out, right? So it supports, but doesn't prove the mechanism that we've suggested. Okay. All right, let's take a look at a different example. All right. So if the rate law of the overall reaction is known, we can use that information to determine whether or not a mechanism can be supported or rejected based on the rate law of our slow step in that mechanism, right? That's what we did in the previous example. That's what we're going to do here in this next one, right? So let's say that we've got the reaction of hydrogen gas plus nitrogen monoxide goes to nitrogen gas and hydrogen or water vapor, right? Now, let's see here. We're going to ignore this for right now. This is not supposed to be here. So we're just pretend like that's not even a thing. We're just going to color over that. We're going to pretend like it doesn't even exist, right? So experimentally, this reaction is carried out and experimental data is gathered, and we see that it's going to be second order with respect to NO and first order with respect to H2. So that means that we're going to have a rate law where rate would be K times NO squared times H2, or K times H2 times NO squared, right? Same thing. So experimentally, this is the experimental rate law. Now let's say that we're provided the following mechanism, right? So experimentally, this is what we found. Does the following mechanism support, or should it be rejected based on the rate law that we've been provided with? So it's a three-step process. We take a look at our 3 steps. And again, the thing that we want to key in on to help us figure this out is we want to identify which one is our rate determining step or our slow step. And so that's our first one, right? So we look at our first step. That's what's going to determine our rate law. So we're going to look at that. We say, okay, the first step is the slow step. And so according to that step, because it's elementary, we can say, all right, according to that, rate is equal to K times the concentration of H2 times the concentration of NO. All right, so when I look at this slow step says the rate's K times H2 times NO. That's not the same thing as the experimental rate law that we were provided with. So that means when we look at that, we're going to say, okay, so because this rate law doesn't match up with the experimentally determined rate law, what we would do is we'd say, okay, this particular mechanism does not support the rate law, so we would reject it. We would say this mechanism does not support the experimental rate law that we've been able to observe. So we would have to look at this and say, okay, we thought this could be a process. This is not a process that's being used here. This is not the steps that this reaction's taking in order to go from reactants to products, right? So in this particular case, this mechanism does not support our experimental rate law, right? And so really that's going to be your task. You're going to be provided with either a mechanism, and you're going to be asked, determine the theoretical rate law, like what we did here. So that what's in yellow was the theoretical rate law. Then you might be provided with an experimental rate law. And then you're just going to be asked, okay, do they support each other? And things like that. You could also think of it as, since this has to be experimentally determined, you could think back to some of the things that we did earlier in this unit of how we could determine orders of reactants based on experimental data. You might have to go through that process and say, okay, this was the experimental data, this is how we got here. And then you could use the mechanism and say, okay, do they match up, right? So that's kind of where we're headed here. And kind of the nice part about the ones that we've done so far is it's been nice and easy. And the slow step's been the first step. There's been no major issues that we've been able to run into. And so the next video, we're going to look at a scenario where, what if your mechanism is a little bit more complicated? And so hopefully this video made sense. If you got questions, please don't hesitate to ask. Make sure to fill out the Google form. Let me know if there's anything that you guys need. But if not, thank you guys for stopping by, and I'll see you guys soon.